Good morning. We're going to continue doing some problems from, chapter 4. Um, no one has called in, so I'm just going to record some problems for a little while. Then I will stop. So I'm going to change my share so you can see the problems. And since there's no one here to ask questions, I'm just going to try to explain these so that you understand what's going on. And remember to pause if you need to and rewind. So let's take a look at this first one here. We'll change the lighting a little bit. So here we have, you can dissolve an aluminum soft drink can in an aqueous base such as potassium hydroxide. So the aluminum in the can reacts with the potassium hydroxide. And of course you have water in the solution already because this is aqueous. But nonetheless, you do need water for the reaction. And you get this potassium aluminum hydroxide. And the reason there are 4 hydroxides is because the potassium has a +1 charge, and that's for 1 hydroxide. And the aluminum has a +3 charge, and that's for 3 hydroxides. So that's why the formula is KAlOH4. And you get 3 hydrogen molecules. So the question here is, if you place 2.05 grams of aluminum in a beaker with 185 milliliters of 0.135 molar KOH, will any aluminum remain? And then what mass of potassium aluminum hydroxide is produced? So here we need to find out which one of these reagents is limiting. And I think it's probably easier to start with the 185 milliliters of 0.15 molar KOH and find out if it will react with 2.05 grams of aluminum. So I'm going to take my 185 milliliters of KOH solution, and I'm going to convert that to liters of KOH solution. And the reason I'm converting it to liters of KOH solution is because this molarity is in moles per liter. Then I can convert that to moles of KOH. And then using the balanced reaction, I can turn that into moles of aluminum. And then finally into grams of aluminum. So here we go. 185 milliliters of KOH times 1 liter of KOH per 1,000 milliliters of KOH. And then times, the concentration is 1.35 molar, so that's 1.35 moles of KOH per 1 liter of KOH. And then the mole ratio are 2 moles of aluminum to 2 moles of KOH. And then finally, we need the molar mass of aluminum, which I believe is 26.28, but I'm going to double check with my book. Well, 26.98. And I'm going to estimate the answer before I plug this into my calculator just to make sure that my calculator isn't too far off. So 185 will go into 1,000 about 5 times. 5 will go into 26, but a little bit more, right? 5 will go into 26.985 times. So now we have 5 times 1.35, which means 5 plus a third of 5, which I'm going to say is around 7. So the answer should be around 7-ish, maybe a little more, maybe a little less. But nonetheless, if the answer is 7 and I only have 2 grams of aluminum, then all of the aluminum should react. So 185 times 1.35 times 26.98 divided by 1,000. And I'm not going to do the 2's because 2 divided by 2 is 1. And I get 6.74 grams of aluminum can react with our 185 milliliters of KOH. So all the aluminum should react because the KOH solution can react with 6.74 grams of aluminum, and the can is only 2.05 grams. All right, so we figured out which one is the limiting reactant. The aluminum is the limiting reactant. So we need to figure out what mass of potassium aluminum hydroxide is produced. For that, we're going to take the grams of aluminum, turn that into moles of aluminum, turn that into moles of potassium aluminum hydroxide, and then turn that into grams of potassium aluminum hydroxide. So we have 2.05 grams of aluminum times 1 mole of aluminum per 26.98 grams of aluminum. And then the mole ratio is our 2 mole of potassium aluminum hydroxide to 2 mole of aluminum. And then the molar mass of potassium aluminum hydroxide, well, potassium is 39, I believe, 39.10. Aluminum is 26.98. 4 hydrogens is 4.04, and 4 oxygens is 68. So when we add these all together, the 98 and the 4 is going to become 0.2. That becomes 40 then. And then 66, 70, 138, if I did it right. Okay, so times 138.02 grams of potassium aluminum hydroxide per 1 mole of potassium aluminum hydroxide. So I'm going to cross this off to get it out of the way, and then I'm going to put equals, and I'm going to estimate again. 26.98 will go into 138 about 5 times. 5 times 2 is 10. So I should get an answer of about 10. And I get 10.5 of potassium aluminum hydroxide. So you would need to show pretty much all of this for an answer like this on the exam. You need to show how you figured out which reactant was limiting, and then you'd have to show how to figure out the mass that you would produce. Okay, so let's put that one to the side. And let's do another one here. What mass of 0.125 molar oxalic acid, which has the formula H2C2O4, is required to react with 35.2 milliliters of 0.546 molar sodium hydroxide? So here we have the reaction, and I'm going to write a little bit of stuff under this reaction. We basically have 0.125 molar oxalic acid. We have 0.546 molar sodium hydroxide, and we have 32.5 milliliters of that sodium hydroxide solution. So what I'm going to do is I'm going to take this guy and turn it into liters of sodium hydroxide. And then I'm going to use the molarity and the liters to get the moles of sodium hydroxide. And then I'm going to take the moles of sodium hydroxide and figure out the moles of oxalic acid. And then I'll use the moles of oxalic acid along with the molarity to actually figure out the liters of oxalic acid. And I think I'm going to leave it in liters because why change it to milliliters? That's an extra step. And it says what volume, but it doesn't say how many milliliters. So I'm going to start with my 32.5 milliliters of sodium hydroxide. I'm going to multiply by 1 liter of sodium hydroxide per 1,000 milliliters of sodium hydroxide. Then I'm going to multiply by the concentration. So I'm going to put the 0.546 moles on top. And the 1 liter of sodium hydroxide on the bottom. Now notice that says moles. It doesn't say M, it says moles, because this M means moles per liter. Okay, now I'm going to multiply by the balanced reaction of 2 moles of sodium hydroxide. That's going to go on the bottom. And 1 mole of oxalic acid. Then I'm going to multiply by the concentration of the oxalic acid. Only here, I'm going to put the 0.125 moles on the bottom. And I'm going to put the 1 liter of oxalic acid on top. Okay, so if we take a look, certain things will cancel. And we'll be left with liters of oxalic acid. So when I estimate this answer, this I think of as being, well, 1,000 times 0.125 is going to be, move the decimal over, what, 3 places, so 125. So 32 will go into 125 about 4 times. So 4 will go into 0.546, about 0.11 times. And then half of that makes it about 0.05 liters. Okay, so let's see what we get. 32.5 times 0.546 divided by 1,000 divided by 2 and divided by 0.125. And I get, oh, I'm off a little bit, not 0.05, but 0.07. 10 liters of oxalic acid. Now, if you don't like that answer of liters, you could always take it and convert it into milliliters. So in this case, it's 1,000 milliliters. Whoops, extra 0 per 1 liter of solution. And I get 71.0 milliliters of the oxalic acid solution. So this is what you want to show at a minimum for your answer, because that is a volume, and that's perfectly fine when they don't ask for milliliters. And if you wanted to do this, that'd be okay too. Okay, the next one. What volume of 0.955 molar HCl in milliliters is required to titrate 9.152 grams of sodium carbonate to the equivalence point? So here we have 2.152 grams of the sodium carbonate, and we have 0.955 molar HCl, and we want to know the milliliters, right? So I'm going to take this, turn that into moles of sodium carbonate, turn this into moles of HCl, and then I'm going to take these two numbers, the moles and the molarity, and get the liters of HCl, and then turn that into milliliters of HCl. So let's see how this goes. 2.152 grams of sodium carbonate Sodium carbonate is 22.99 plus 22.99 plus 12.01 plus 48. So if I add these two numbers together, I get 60. 60 plus 44 is what? 104 plus almost two more, so that's 105.01. No, 09. Yeah, seems about right. Let's see. That would be 9, carry the 1. So 0.99. And then carry the 1. And that becomes 10, 15, carry the 1, and that becomes 10. Okay, so times 1 mole of sodium carbonate per 105.99 grams of sodium carbonate. Now, next, I'm going to use the stoichiometry of the equation, which has 1 mole of sodium carbonate to 2 mole of hydrochloric acid. So 2 mole of HCl and 1 mole of sodium carbonate. And then I'm going to use the molarity here. And so I'm going to put the 0.955 moles on the bottom and the 1 liter on top because I need the moles to cancel. And then lastly, I'm going to write that there are 1,000 milliliters of that HCl solution per 1 liter of HCl solution. So I have everything set up. I'm going to estimate the answer. 105 will go into 1,000. Well, actually, let's do this. 105 times 0.955 is 100. 100 goes into 1,000 10 times. 10 times 2 is 20. 20 times 2.152 is 42. So the estimate is 42. 2.152 times 2 times 1,000 divided by 105.99 and divided by 0.955. And my estimate is way off. I got, what did I say my estimate was? Oh, my estimate wasn't that far off. I got 42.5. And we're limited to 3 significant figures because it's 0.955. So that's the kind of work you would be expected to see for this titration. Okay. Do another one. So here we have potassium hydrogen phthalate. And here's the formula. This isn't quite the way we wrote the formula for our lab. To put the hydrogen out here, because that's an acidic hydrogen, we had H5. Is used to standardize solutions of bases. The acidic anion reacts with strong bases according to the following ionic equation. So here's the anion, reacts with the hydroxide ion, and you get this, which is called the oxalate ion, and H2O. So an acid and a base gives you a salt and water. Now, you might wonder, well, that's not a salt, but you got to remember that this is probably potassium and potassium hydroxide. So you've got 2 potassium ions here, and this is really potassium oxalate. So that is a salt. If a 0.902 gram sample of potassium hydrogen phthalate is dissolved in water and titrated to an equivalence point, what is the molar concentration of the NaOH? Okay, so we have a 0.902 gram sample of potassium hydrogen phthalate. So I want to put 0.290 grams here, but that's not correct. That's hydrogen phthalate. This is 0.902 grams of potassium hydrogen phthalate. So I'm going to abandon writing things underneath here, and I'm just going to write from here what I need to do. Now, I can turn that into moles of potassium hydrogen phthalate. And then if I really want to use this equation, I might want to turn that into moles of hydrogen phthalate. Oh, and that's supposed to be a 4, and a 4 there, and a 4 there. Okay, so here I can do that and that because I have the formula right there. Then I can turn that into moles of hydroxide. And then here with the molarity, with the milliliters of this, well, I will say this is one of the things I'm going to need. And then I'm going to take the 26.45 milliliters of sodium hydroxide and turn that into liters of sodium hydroxide. That way I can take this number and divide them to get the molarity. So let's see how that works. So 0.902 grams of potassium hydrogen phthalate. The molar mass of this guy, potassium is 39.10. Hydrogen is 1.01. 8 carbons is 8 times 12.01, which is 96.08. And then 4.04 for these 4 hydrogens, and 64. Whoops, I made a mistake. Plus 4.04, and then plus 64. So I get times 1 mole of potassium hydrogen phthalate per 204.23 grams of potassium hydrogen phthalate. Now, 1 mole of HC8H4O4 to 1 mole of KHC8H4O4. And then I have 1 mole of hydroxide to 1 mole of oxalate ion, or hydrogen oxalate ion, I should call it. And I'm going to put in one little extra thing that I didn't have up here, and that is going to be 1 mole of sodium hydroxide per 1 mole of hydroxide. So that should give me the moles of sodium hydroxide. And if we take a look at these are all 1s everywhere except for this, 0.9 divided by 200, which is about 1 divided by 200, which is going to be a really small number. 0.902 divided by 204.23. And indeed, it is a really small number, 0.004417. And really, I should be rounding to the 1, but I'm not going to right now. And that's moles of sodium hydroxide. We take our 26.45 milliliters of sodium hydroxide, multiply by 1 liter of sodium hydroxide per 1,000 milliliters of sodium hydroxide. And we have 26.45 divided by 1,000. And I get 0.02645 liters of sodium hydroxide. Now I'm going to take these two numbers and together calculate the molarity. So we have 0.004417 moles of sodium hydroxide per 0.02645 liters of sodium hydroxide. And remember, with this top number, I really only get 3 significant figures. So my answer here will be 3 significant figures. And our answer is 0.167 molar sodium hydroxide. So we would expect to see all of this work here for this answer. Okay, let's see if we want to do one more. What I'm trying to do is finish off all the problems in the book that hit before the general questions. And so I'm going to check the book real quick. Titrations end at number 76. So here is number 76. And this will be the last problem that we'll do for this particular session. All righty then. Vitamin C has the formula C8H8O6. Besides being an acid, it is a reducing agent, which means it gets oxidized. One method for determining the amount of vitamin C in a sample is to titrate it with a solution of bromine, an oxidizing agent. For our lab, we tried to use a different oxidizing agent because this solution is kind of nasty. Okay, so nonetheless, here's the reaction. And here, this is what the vitamin C turns into. And here you can tell that it's been oxidized because it has lost hydrogen. You can tell this one has been reduced because it has gained hydrogen. That's another way to tell if you have a redox reaction, is if certain things gain hydrogen and other things lose them. A 1.00 gram chewable tablet of vitamin C requires 27.85 milliliters of 0.102 molar bromine for titration to equivalence. What is the mass of vitamin C? So I think I'm going to take the 27.85 milliliters of bromine, and I'm going to turn that into liters of bromine. So why am I doing that? And the answer is because molarity is moles per liter, not moles per milliliter. So if that's moles per liter, I want liters of bromine. Then I can use the molarity to get the moles of bromine. And then from the balanced reaction, I can get the moles of vitamin C. So that's vitamin C right there. And then I can get the grams of vitamin C using the molar mass of vitamin C. So let's go about doing this. 25.85 milliliters of Br2. What's the conversion for milliliters to liters? Yep, you got it. 1 liter of Br2 to 1,000 milliliters of Br2. Now this is the molarity. We have 0.102 moles of bromine per 1 liter of bromine. So I'm going to put the 1 liter of bromine on the bottom and the 0.102 moles of bromine on top. And then we need the mole ratio. Here we've got 1 mole of bromine to 1 mole of vitamin C, which is C6H8O6. And then we need the molar mass of vitamin C. Six carbons, 6 times 12 is going to be 72.06. So that's 6 carbons, 8 hydrogens, and 6 oxygens, which would be 90, let's see, 96. The way I'm doing the 6 oxygens is that 2 oxygens weighs 32, and I have 3 of them when I have 6. So 32, 32, 32 is 96. So here we get 14 there, 10, 6, carry the 1, and we get 17. 176.14 grams of C6H8O6. And I'm going to estimate the answer to make sure I don't mess up with my calculator. 176 will go into 1,000 5 times with some left over, right? So let's call it 6 just for fun. 6 will go into 27.85, almost 5 times. 4 times for sure, but maybe 5. And the reason I'm saying maybe 5 is maybe this number shouldn't be 6. So we have 4 to 5 times 0.102, which means the answer should be around 0.5-ish. Okay. So clear, 27.85 times 0.102 times 176.14 divided by 1,000 is equal to 0.500. And here we only get 3 significant figures because of this number right here. So we get 0.50. I'm going to write it down here. 0.500 grams of vitamin C. So this is the work I'd expect to see, not this, for an answer for this one. Okay, so that's all of the problems from the end of the chapter that are not in the general section. There are some more problems in the general section that we could do, and we'll see. Okay, hope you learned from this film, and thank you for watching.